Hello everyone, and welcome back to Virtual Thermodynamics. In our last class, we looked at an example for a basic Rankine cycle with 4 components. So if you haven't watched that video, it might be a good idea to go back and check that one out first. In that video, we found that for our 4-component Rankine cycle, we had a thermal efficiency of 28.4%. You might be thinking, well, that's kind of low. Even if we think about a Carnot cycle efficiency, which maybe, I didn't check in this case, but maybe somewhere around 50%, right? So what we're going to try to do today is look at how we can go about increasing that efficiency. Why should we improve efficiency? Well, there's 2 reasons. The first is that if we're improving efficiency, we can get the same power out without putting in as much heat, right? So we're saving money, right? But another reason that we might want to improve efficiency is that if it means that we're burning less coal, for example, then that means we're creating less emissions. And that's good for those of us who like living here on Earth. Right? So how are we going to go about increasing efficiency? Right? And the answer is we're going to go from this kind of basic Rankine cycle, right, which was us sort of, looking at these cycles as almost like Lego blocks, right, but something that's more simple, right, maybe like a Duplo type system to, we want to be master builders, right? So we're going to start adding components and see if we can use that to improve our cycle efficiency. So the first way we're going to do that is with something called Rankine reheat, right? So in this case, we're going to add a second turbine. So we have a high pressure turbine. That's the first turbine that our fluid is going to go through. And then a low pressure turbine. And in between those turbines, we're going to take our working fluid, run it back into our boiler or steam generator, and we're going to add some more heat. And in this example, we'll see if that improves our cycle efficiency. So in this case, when we look at the thermal efficiency, it's still going to be the same conceptually, where we talk about the net energy benefit divided by the heat in, right, or the energy cost. And our net energy benefit is our net work. But here we have to remember that our net work now includes the power generated by 2 different turbines, and we still only have 1 pump, so there's only one thing consuming power. And then when we look at heat added into our system, we have we may have only 1 steam generator, but we're adding steam in 2 different processes, one as we move from state 6 to state 1, and the other as we move from state 2 to state 3. We're still going to use a first law analysis on all of these different components. And when we do that, we're going to get the same equations that we did last time when we worked on just a typical or a sort of 4-component Rankine system, right? So for turbines, we're going to have m dot times h in minus h out. We'll do the same thing for pumps, and we'll let the first law tell us if we're consuming power or if we're generating power. And if we're looking at some kind of a heat exchanger or a process where we're doing some heat transfer, we're going to have m dot times h out minus h in. And then we got to ask ourselves what the fluid, and for Rankine cycles, again, this is typically water, but it's certainly something where we have a phase change or where we're crossing over the vapor dome. In this problem, we're given, again, some kind of a state table here to start with. Notice that as we start to add components, we're also adding more states, which might mean that we have to look more things up in tables in our textbook. But some of these states we've already done, so it shouldn't be too bad, hopefully, if we've already done our first example. So our thermal efficiency for the reheat, we talked about this already. This is going to be the net power divided by the heat in. Unfortunately, we don't know the power that's being generated by either of our turbines. We don't know the power that's being consumed by our pumps, and we don't know the amount of heat that's going in our heat exchange processes. So it's nice that we have a symbolic solution, but we don't have any of the information that we need to solve the problem. We'll do a first law analysis everywhere. We've talked about this a little bit already, right? We'll make these same assumptions that we talked about. And we get these equations, now specifically for our high pressure and low pressure turbines, for our pump, and for our two boiler processes. So now we can put this all back in to our equation for thermal efficiency, right? But first, it might be worthwhile to look at conservation of mass. I didn't explicitly do this in the last example. But here, if we're at steady state and all these components have one inlet and one outlet, what that means is for each component, the mass flow rate in is equal to the mass flow rate out, which means that there's only one mass flow rate in the problem because all of these components are kind of lined up one after another. So there's only one mass flow rate in our problem. So when I substitute my equations from the first law in for the power or the heat from our components, I see that the mass flow rate terms all drop out, and I get that the thermal efficiency for my reheat cycle is a function of the specific enthalpies throughout my system. I know H1, I don't know H2, I know H3 but not H4, I know H5 but not H6, and that's still true in the denominator. So I need to fix some states in order to find the thermal efficiency. We talked about this last time, but we can find our isentropic efficiencies. For the turbine, we have the real power over the ideal power, right? So I can get an expression for the specific enthalpy at the real outlet of the turbine, right? But in order to do this, now I need to know the heat out and the ideal turbine, right? So I know that when I get to state 2s, my specific entropy has to be constant because this is an isentropic process. Right? So now if I have state 2s, I can find H on my tables, right? So I know what the pressure is. I know what H2s is, or S2s is 6.88 about. Right? So I can do some linear interpolation, finding some constant A. It's just about 1. So I could probably just read off from the line 240 here, but I can also do some linear interpolation, and I can find H2s. So that's good. I know H2s. I can try to find H4s here too, the other isentropic process. Right? So again, I know that S is constant. So I'm going to do the same thing. So this is going through my low pressure turbine now. Now I see that if I look for S2 now at the temperature that's given here, then what I find is that 2s is, or S2s is in between SF and SG. So that means that I have a two-phase mixture here. So what I need to do is I need to find my quality of my fluid. So how much is vapor here? And again, this is almost all vapor, but a little bit of liquid water. And then once I find X, then I can find H4S, which in this case is 2,626. So that's good. I know the ideal outlets of both my turbines, but I need to find the real outlets as well. So now if I use my isentropic efficiency equation, I can get expressions for the real outlets, right? So here, my real outlet of my first turbine is H2. So if I put the information that I know into this equation, I can get a value for H2 and a value for H4. I can put these back in my state table, and now I'm feeling pretty good because I have H's except for H6. H6 is always tricky because this means that we're running through a pump. So first I got to look at the isentropic efficiency of the pump. In this case, I have the ideal power over the real power. I need to find the outlet enthalpy, and I can isolate that and find it. And I see that H6 is 407.3. Remember, for the ideal pump, I have to use the specific volume multiplied by the change in pressure, and I need to check my units when I do that. Again, we did that in the previous example if you want to see how to do that. So this is good. So I know all my H values, and now I got to try to find my thermal efficiency. Thermal efficiency, oops, animating in the wrong order here. But if we get our thermal efficiency, we can put numbers in here for all of our delta H's. And when I put all those numbers into my calculator, I find that I get a increased efficiency here of 29.2. If you remember, our previous efficiency was 28.4. And it might not seem like a lot to only increase the efficiency by a percentage point, but when we think about a power plant that's running all the time, then if you're increasing your efficiency by 1%, you're actually saving a lot of money because you're burning less coal, and that means that you're also saving emissions as well. So it really does make a difference. Thanks again for joining Virtual Thermodynamics, and I'll see you again next time.